Today we are going to learn the topic on thermoregulation. Now this topic comes under the paper on thermodynamics of living systems and bioenergetics. Now in this unit the major objectives of the course are that various mechanisms of heat loss. Now physics aspects as well as physical chemistry aspects of heat related to radiation, evaporation, conduction and convection. In addition to that, you are also going to learn about the heat production mechanisms in the human body. Now what is the role of skin, various organs like muscle, central nervous system, all these things we will be trying to understand their role in thermoregulation. And later we will be studying the thermoregulation particularly in the infants, newborns, as well as how is it important and why is it so critical. And after that we will see how the animals maintain their temperature, that how do they maintain their body temperature, and both in case of the ectotherms as well as endotherms. And finally, after doing all the topic, you should be able to solve the problems based on the equations and the subject based on the topic that is taught to you. Now the first thing is, what do you understand by thermoregulation? Now that word is very clear, that regulation of the body temperature. Now how does a body temperature maintained? Which means that there has to be a balance between the heat loss and heat gained. Okay, so that in some textbooks you also find that thermoregulation also is called as temperature homeostasis. Now what do you understand by homeostasis? Homeo means that maintenance, stasis means that it has to be constant. Now that could apply to any parameter, but here we are talking about temperature homeostasis. So literally when you talk about homeostasis, which is actually described as a property of any system in which the variables are regulated so that the internal conditions, that means here the temperature, remain stable and relatively constant. Now core temperature of the body is of the human body is actually maintained at 37 degrees centigrade. We all know about it, and if you look at the other temperature unit, that is a Fahrenheit, 98.6 degrees Fahrenheit. However, it is not that exactly one temperature it will maintain. There is a short range, that is within that range the body temperature is maintained. For example, if we talk about the degree centigrade, it is between 36.5 to 37.5, and that translates into 97.7 to 99.5 degree Fahrenheit. Now when we say the core temperature of a human body, what are these? What is a condition under which this body temperature is maintained? When we say it is a normal physiological conditions, in addition to normal physiological conditions, what we say is that the body should be without any exertion. You are not doing any exercise, you are relaxing, like the way you are watching the TV now or the monitor, you are sitting and then relaxed. So it has to be under very not stressful condition with no exertion, and of course it could be between in a sleep also, in a deep sleep, or under any resting condition. In addition to that, that body has to be comfortable and also in a healthy state. There should not be any, you may be physically very comfortable, but internally you may be having a fever or any other unhealthy state. That is not the normal temperature. So the core temperature of the body, when we say 37 degree or 98.6 Fahrenheit, is actually under normal healthy physiological conditions when person is in a very comfortable situation like resting or sleeping. But we all must have faced some time or the other in our life that our temperature of body temperature goes up. For example, in fever, which is very common, or when you have some kind of infection, stomach infection, the temperature can go up. Now that is called hyperthermia. Hyper means higher than the normal condition. So now higher means the body temperature rises above the normal temperature, For example, as I just told, it could be several other disease conditions like stroke. There are many more. It can lead where the temperature can go up. Now, when the temperature actually rises to 105 to 107 degrees, that is really severe and critical, and it can be life threatening. Under normal conditions, you can take a paracetamol, the temperature comes down in addition to other medications. But when it is very high, it becomes really life threatening, and body's mechanism of regulating really becomes very difficult. Now, on contrary, you have hypothermia. As the word says, hypo means less, that the body temperature goes down the normal temperature. Now, what are these conditions? That any temperature less than the 98.6 Fahrenheit is actually called a hypothermia. But hypothermia again can have variations or the degrees of hypothermia. It could be very mild. Sometimes you are not wearing proper clothing, then you may find it very mild, but when it comes back, it recovers very fast. Or it could be a moderate. Now, when it is a mild, it is 98.6 to 96 degree Fahrenheit. Or it could be a moderate hypothermia where the temperature goes up to 95 to 93 degrees. Or it could be again severe, very critical, that is severe hypothermia, again needs doctor's intervention, and that time the core temperature actually falls down to as much as 80-60 degrees Fahrenheit, and therefore this again is a life threatening. So, now you have seen that although the body temperature is maintained most of the lifetime, but then temperature can go up or down under critical conditions. Now, what happens actually? Why do the temperature of the body goes down? That leads to hypothermia. We all know that sometimes we are not properly wearing woolens under severe winter conditions, cold temperatures, that can temporarily bring down the body temperature. And also, if you are under a very freezing conditions, that is below zero, sub-zero temperatures, and you go there without proper equipment and proper woolens, again it can go into hypothermic conditions. And you must also have seen that if you are wet in rain and the ambient temperature is not very high and you stay in the wet clothes for a very long time, body temperature can go down because it is not able to control it so well, because it is exposed to low temperature for a longer period. And main thing is a fatigue. If you are exerted for a very long time, exhaustion can lead to hypothermia, dehydration. There are some other factors. Poor food intake, you are in winters and you don't have enough carbohydrate to give you energy, again it can lead to hypothermic condition. Old age people, you must have seen that old people feel cold very easily because their internal temperature is controlled in a very different manner. And also these things can lead to, all these conditions can lead to actually the peripheral circulation problems like blood circulation problems, and also can teach to trench foot and also frostbite and things like that. These are some of the clinical manifestations to hypothermia. So, after seeing these things, that now we would like to know what actually the main reasons under which the body temperature is regularly maintained without even our knowledge. That is the nature of a living organism. In humans, it is maintained in a different manner. Animals, it's kind of a different, and in plants and so on. Even within each organism, it is different. Now, age is one of the important criteria. As I just mentioned you a short while back, that the old age people have really feel very, they are very vulnerable to low or high temperatures. Similarly, the newborns mechanisms have not really developed, and therefore they need a kind of real understanding and maintaining the body temperature, which we will be dealing with it in the next unit, that is the next module. And other factors are the body surface area, then the body mass and hormonal levels really control the body temperature. Now, the metabolic state, physical activity, these are two are also mentioned in my previous slide, that circadian rhythms, the night temperatures during the night, during the day and during the afternoon, depending on these hormonal levels and circadian rhythms, the body temperature can really be influenced. Then the external temperature, you are in a very hot condition or in a freezing condition, then of course internal mechanism, that is infection or any kind of a pathological state, all these can really influence the body temperature. Now if you really look at it, I mean, it's interesting to note that most of the organisms, whether it is humans or any other living organisms, actually on the geographically if you look at it, they are all in the most of them live under between a certain temperature, that is very narrow temperature range between 10 to 30 degrees centigrade. This is actually very interesting. So if you see the screen, that the central region on the globe, that is red, which is the most of the organisms do live. Of course there are people who organisms which live under Arctic and Antarctic and very hot temperatures, but that's very interesting to note that most of them live under 10 to 30 degrees centigrade. So after understanding that the body temperature is maintained so well, now the question comes that how is the body regulating its temperature? It's a simple phenomena that there is a real the real critical way of maintaining the heat loss and heat production. So there has to be a fulcrum maintaining the heat balance, that is the important part, and that is how it is maintaining the body temperature. Now what is the mechanisms of heat loss? Evaporation, radiation, conduction and convection. Now when you compare the other side, what are the mechanisms of heat gain? Obviously body is producing heat because the metabolism, and you are eating a lot of carbohydrate which give the heat, convert it into glucose and then to ATP, and you get a heat production. Also when you are doing exercise, it produces heat because metabolic rate is very high, and also shivering under the low temperature conditions, under freezing conditions, the body has evolved a very nice mechanism that even if we do not have much winter clothing, but tries to maintain or come up with mechanism which is the shivering mechanism. This is actually one way to help to regain the body temperature to normal. And then of course external heat. If you are externally warm in a winter, you have the heaters or air conditions, that also can help in the external heat conditions. So if you look at the major loss of heat, that is by the radiation. Now that radiation is coming from the sun, for example. Now the second phenomena is the evaporation. For example, you can see that sweating is one basic and natural phenomena of losing the heat, and also convection. The convection currents around you, the air that is around you actually takes away the heat from you, and of course the conduction. In conduction, you are directly in touch with the heat, so body can pass the heat very easily. So these are the basic four mechanisms by which the heat loss by the body occur. Now that is under normal conditions, but suppose you are doing an exercise, the basic phenomena still remain same. However, there are a couple of things which actually are add more to the heat loss mechanisms. That is the natural convection, that is a body. However, in addition to that, you have forced convection. For example, you are running on a or exercising. During that, your foot is actually all the time moving and putting pressure on the ground. So there is a forced convection, and that adds to another loss of heat mechanisms. And similarly, your exhalation of the warm and moist gases is higher when you are doing exercise. Radiation and of course conduction, other things remain natural. So if you see the figure, that a person running undergoes removes the heat from the body by these mechanisms. So when we look at the heat loss mechanisms, the body is involved in heat loss using a different organs. For example, if you look at the radiation, the skin is a major organ, and then when you look into the convection, then it is actually both smooth muscles as well as the skeletal muscles are involved. For conduction, again skin, And in evaporation, both skin, sweat glands are involved, and also lungs, because lungs exhale the gases, evaporate. And therefore, under normal conditions, all of them are working normally. However, when you are exposed to high temperatures, the radiation by mechanism is not very important. It plays a small role, whereas in case of the convection, it is very high, and here the smooth muscles are very important, and therefore by vasodilation the heat loss occurs. Similarly, in conduction also is very high, and the surface blood flow will be very high. Flow is one of the reasons that heat is lost. Again, evaporation, it is also high, and increase in the sweat is one of the ways that the heat is lost at high temperatures. Again, on contrary, when you see the low temperatures, the radiation is not very high, it is very clear, and there, whereas a convection is low and the skeletal muscles actually play vasoconstriction role, and in conduction is also low. Evaporation obviously at low temperature is low. So these are the things that by 4 mechanisms play role using different organs, like for example skin, lungs, as well as skeletal and smooth muscles. So after getting familiarized with these terms, radiation, convection, conduction and evaporation, we will discuss in more detail each one of them. Firstly, we'll do the radiation. Now, what do you understand by radiation? Radiation can be put in simple terms as a form of energy which comes from one source and travels through a medium. The medium can be air, water, a liquid, or even space. So, for example, sunlight coming from the sun to reaching the earth is radiation. Now, similarly, the light coming from a bulb is having light radiation and a small amount of heat. Similarly, the bell which gives sound is also a form of energy and travels through a medium, that is air. So, all of them can be considered as radiation. Now, when I talked about all these are generally called non-ionizing radiation, because they do not give any ions when they travel through this medium, any medium. But you also must have come across the term called ionizing radiation. That means, for example, alpha rays, beta radiation, gamma rays. So these are ionizing radiation. So when we talk about radiation, there are 2 types, one is ionizing and the other is non-ionizing. So ionizing radiation, we will do it in much more detail in another paper, but here we will only be doing the non-ionizing radiation, for example, light, heat and sound, as I just showed you in those pictures. So when we talk about radiation in connection with the human body, is human body radiating any energy? The answer is yes, but you do not see anyone radiating with light. That is because it is not in the visible range. So when we talk about visible range, what do you understand by visible range? So it is actually electromagnetic radiation. Now the electromagnetic radiation can be starting from a very high energy with gamma rays and go into a low energy up to the AM. So the infrared rays in between is a range in which the human body actually emits. So this is a very small energy, and therefore it could be considered as 0.75 to 1000 microns, or that is the frequency, what wavelength we are talking about. So it's a very small amount of radiation. So if you look at the spectrum, actually starting from the ultraviolet to these UV rays, this is the human body, actually how the spectrum of the emission by a human body. This is just to show you that the frequency is very high in the ultraviolet range. So after understanding the human body radiation and its spectrum, let us calculate that how much energy the body actually emits. So when you want to determine the energy that is emitted by a human body, what we can express it in terms of power, that is a net power, the total power. So the total power you can calculate using the Stephen-Boltzmann law. Now what is the Stephen-Boltzmann law? P, the power emitted by the human body, is equal to A is the body surface area expressed in meter square, and E, that is the emissivity constant, that is usually 1, considered as 1, and sigma, the Stephen-Boltzmann constant, which is given on your screen, that is 5.67 into 10 to the power minus 8 W power m square minus 2 and k to the power minus 4. Now, T is actually the temperature. The temperature is expressed in degree Kelvin, that is absolute temperature. So, if the body temperature is 37, then it is 37 plus 273 degrees Kelvin, that is the total is 310. Okay. So, this is the equation where you can determine the energy or the power that is emitted by the human body. So, let us calculate and just see that if the body temperature is T and the ambient temperature, that is the surrounding temperature, is T ambient. So, when you calculate the net power, that is how much is given out, the net power can be calculated as P net, which is A into E, same equation, E into sigma into T to the power 4 minus T power 4 ambient. Okay. So, for a human being, again we consider it as 1.2 meter square as a surface area. E is a constant 1, approximately 1, and the ambient temperature is, say for example 22 degrees, like in AC room it is comes 273 plus 22, it is 295, and of course the body temperature 37, so it becomes 310 degree Kelvin. So, in that condition, that P net, which can be positive or negative depending on the emission of the radiation of the body. Now, that will be the net power dissipation by the average human body is about 81 watts. Okay. So, that is the normal conditions. Now, having done this, let us do an example where a human body temperature is 40 degrees, for example, in under pathological conditions like a fever or infection, that is 40, and then he or she is admitted in a hospital. So, the hospital temperature is 24 degrees centigrade, and now you have to use A, that is a surface area, as normal 1.2 meter square for example, and emissivity constant as 1 and Boltzmann constant. Now, you should be able to do this again on your own using the Stephen-Boltzmann constant. Now, the solution I have shown you are 4 options. Okay. A 22, B 22 watts, C 24 watts, D 40 watts. Now, I do not know what you have got, but suppose you got an answer of 22 and you left it like that, your calculations are right, but since you have not given the units, you will lose 1 mark, and it is very important to mention the units, because the power is expressed in watts, or you can even express it in joules per Kelvin. And second one is the B, that is 22 watts. If you have given this answer correct, very correct, you have got full marks. But if you got the third answer 24 watts or the fourth answer 40 watts, there is something wrong in your calculations or your understanding. So, you should go back and check with your original equation. Now, so far we have understood the role of radiation, how a body emits radiation and how much power it emits radiation. Now, at this stage, what in medicine, what it has been used as a diagnostic purpose. So, this is what is known as thermal imaging. In 1800, the IR actually spectrum was discovered by Sir William Herschel, and then his son later John created the first thermal image based on Sir William Herschel. Now, this imaging is used as a diagnosis. No doubt that it cannot be used alone by an isolation. It is usually used in connection with or in accordance with the X-rays, but nevertheless thermal imaging is a very important and useful tool to diagnose disease. I will recall the figure that I have shown you earlier, that the human body actually emits the radiation infrared. So, when you look at the imaging of a human body, you see on the right that patches of red, green and blue. Now, what are these colors indicate? The scale is given there on the right. The red 30, higher temperature 33 degrees and lower the temperature, the color code changes up to light blue. So, if you see that actually the human body itself does not have all the body, the core temperature is high, but peripheral can be different. Similarly, you see a hand showing that the palm has a higher heat energy, whereas in different areas. So, these changes in behavior of the changes in different organs can be used for the diagnostic purpose. Now, these are the examples I am just giving you. For example, breast abnormalities, there is a cancer or any abnormalities, can be seen that if there is a red color compared to the right one, you see the left one has a red color, which is showing that there is something different which is not normal. That is why the heat area, thermal heat is more on that side. Similarly, thyroid, the second picture, and the third, the peripheral vascular disease, you see the tips of the fingers are again red in color, showing that these areas are much more heat producing, which means the metabolic rate is high for various reasons. And again, cerebral vascular diseases, or the knee or the skeletal muscle, or even an inflammation which has a neoplastic condition. Neoplastic means cancer conditions. All this can be seen in thermal imaging. It is a very simple tool and can be understood. However, it is very important that thermal imaging cannot alone in isolation should be considered as a diagnostic tool or a confirmatory tool, but it has to be used in complements to the X-ray tool, and also information provided by the X-ray as well as the thermal imaging in conjunction actually used for diagnostic purpose. So, with this we finish the understanding of the human radiation and the human body, and of course the diagnostic tool with the thermal imaging.